Okay, let's take a look at these heat transfer problems. A couple of pieces of information: brass is at the top, zinc's at the top, and on the back of the sheet, we have the heat capacities for several different solids, liquids, and gases, and we have the latent heats of fusion, latent heats of vaporization. One that's missing here for liquid is water, but you need to memorize that one. That one's 4,200 joules per kilogram degree Celsius. Let's take a look at the first questions. Well, they're just converting back and forth. Kelvin has no negative numbers, so Celsius, you add 273 to any value of Celsius, you'll get Kelvin. If you subtract 273 from any Kelvin number, then you'll get Celsius. But let's take a look at number 3. It says how much heat in joules is needed to raise the temperature of 50 grams of water from 4.5 to 85 degrees. So number 3. Q just stands for quantity of heat equals the mass of the substance times the heat capacity of the substance times the change in temperature of the substance. Sometimes you could just pull this stuff right out. We got 50 grams. Kilograms water is 4,200. And the change in temperature, 4.5 to 83, that's up. So it's positive, or it's also final temperature minus initial temperature. And that's in degrees Celsius. Degrees Celsius here will cancel. Kilograms will cancel, and we're just left with joules. So 0.05, 4,200, 83 minus 4.5 is 78.5 times, we get 16,485. That's the amount of heat it takes to heat up just 50 grams of water that much. Question 4 says, how much heat in joules must be added to 50 grams of aluminum at 25 degrees to raise its temperature to 125? Same question again. Okay, it's 50 grams again. And the C value for aluminum on the back of the sheet here, solid aluminum, is 900. In the textbook, I think it says 910, so you're going to get different answers depending where you get your numbers from. But if I put 900 in here, change in temperature 25 to 125, I think I can do that one in my head. And now we're looking at 0.05 kilograms times 900 times 100. It comes out to 4,500. I see the answer says 4,550, so that one, when I took this question up originally, we were using the textbook instead of the chart. Number 5. Suppose the same amount of heat needed to raise the temperature of 50 grams of water from, here they go with their scientific notation, one times 10 to the 2 degrees Celsius, so that's 100. So it goes from 0 to 100, so they're going to heat it up. So if we found out how much heat went into the water, it's 50 grams of water. Heat capacity of water is 4,200, and the temperature change was 100. 0.05. That means that 21,000 joules of energy went into the water. And I said, how much temperature change would that give if you put it into zinc? Zinc's numbers here at the top is 388. So it's the same formula again. MC delta T, we have the Q. And the mass of zinc, same mass again. But the C for zinc is 388. And delta T is what they're looking for. They're saying, what's the temperature change? So we just solve for delta T. The 2100 is already on my screen from the last question. And we get 1082. Okay, let's go on to number 6. 6 says copper wire has a mass of 165 grams. Electric current runs through it for a short time. The temperature goes from 21 to 39. What's the quantity of heat? That's why it's called Q. The mass of copper is 165. Oh. And the C for copper is 390. And the temperature range was 39 minus 21. It went up 18 degrees. So multiply all that together. and I got 1,158. Okay, let's continue on with number 7. Number 7 says 500 gram sample of water. 92 is mixed with 500 gram sample of water at 32 degrees Celsius. Find the final temperature. So that means that Q of something that's gaining the heat, like a negative Q of the one that's losing the heat at a loss. Q loss will be a negative number, but negative times negative makes it positive, so everything works out. Mathematically, we know the numbers are the same, but humans sometimes forget the negative sign when we're doing a math formula. Okay, I'm going to separate the page. That side's loss, this side's gain. I don't have to write down M loss, C loss, delta T loss, or gain. I could just fill in the numbers here. So let's put this on the left. So 500 gram sample of water. And it starts at 92 degrees. And now let's go to the negative side. It's another 500 grams. And it's water again. And it's T final. I have to look up, but it starts at 32. Okay, there's our formulas. If there's anything you can cancel, well, yeah, there is. The mass is the same. The heat capacity is the same. So before we wildly jump into this stuff, it's going to be T final minus 92 equals negative T final minus 32. Better expand through the brackets there. Negative TF plus 32. Let's take the T's over there. That becomes positive 92. 92 plus 32 is 124. A whole bunch of algebra here. Divided by 2 is 62 degrees Celsius. Okay, that's the final temperature there. Such that the gain in energy, if we did the math and figured all this out, we get a value of energy, would be the same value of energy on that side. Let's take a look at number 8. A 200 gram sample of brass at 100 degrees Celsius. So we got brass, and that's at the top of the page, is 376 joules per kilogram degrees Celsius. And it's at 100 degrees. And what are they going to do with it? They're going to drop it into water. 261 grams of water. And it's, well, you know that one's 4,200. And its initial temperature is 20 degrees. And they want to find out what's the final temperature of the mixture, because they're both in the same container here. So if we slide this up a bit. So we got, sometimes I even draw a picture. And we're going to mix these two guys together in here. So you could put all your givens here. This is the 200 grams of brass. This is my T final, which I do not know. Water starts at 20 degrees Celsius. This starts at 100 degrees Celsius. And they meet somewhere in the middle. So you can set up, this side here will be losing energy equals. Okay, so there we go. So then we just plug in all our numbers. If this is a test, I give you marks for the givens, I give you marks for writing down the initial formula with the letters, and then we sub them in, and the whole algebra thing is probably only like 1 mark. So you get lots of marks for setting things up here. So that's minus 0.2376 T final minus 100 equals the mass of the water and the heat capacity of the water. Okay, now we got a bunch of algebra to do. 0.2376 is 75.2. Over here, 0.261 times 4,200. That's 1,096.2. TF minus 20. Okay. Let's take it up to the top. we'll continue it here. So this would be minus 75.2 TF plus 7520. Just double check my math, good. Equals 1096.2, enter times 20, plus minus 21,924. Let's collect some terms. I can take the TFs over there so they're all positive, bring that guy over there so he's positive. Equals 1096.2 TF plus 75.2 TF. So let's go 7520. This side is now 29,444. And this would be 1171.4 TF. Divide that into that number. And we get TF equals 25 degrees Celsius. If this was a 5-mark question, you would have 4 marks already when you get to here. Okay, so the rest of it is just doing all the math algebra stuff. Okay, so let's take a look at question 9. Okay, question 9 says, a 100-gram sample of tungsten at 100 degrees Celsius placed in 200 grams of water at 20 degrees. Calculate the specific heat of the tungsten. Okay, that's nice. So now we got a piece of tungsten. It's going to drop into some water. Mix them together. And the T final is going to be 21.6 degrees Celsius. And we had 20 degrees Celsius water, 200. And we had a chunk of tungsten. And we're looking for the C value. It's unknown, but the initial temperature is 100 degrees. Okay, so this one's going to be the loss side. And the water is going to gain. So that's a negative Q loss. So that'd be negative MC delta T for the brass, not the brass, what is it? Tungsten, will equal MC delta T for the water. So let's fill in what we know. 1, C value is my unknown. And it went from 100 down to 21.6. So that's negative. And the water is 0.2, 4,200. And its change in temperature was up 1.6 degrees. So I just have to isolate for C now. These cancel out. So let's find out what the right side is. 0.2, 4,200, multiply 1.6. So the right-hand side is 1,344. I'm going to divide by 0.1, and then I divide by 78.4. And I get a C value of 171.4. So, all right. That's question 9. Okay, let's move on to number 10. Number 10 says, how much heat is added to 10 grams of ice at minus 20 to convert to steam at 120 degrees? Okay, this is another big question. These are the final temperature question of this guy. So this one starts at minus 20, and this question ends at 120. We don't care about anything above or below that, but significant things happen in between there. I know water melts at 0. We can call it ice if you want, but it's still water. So it's going to go up, hit that plateau, and then it's going to stay at 0 till the last little chunk of ice melts. And then the liquid water is going to heat up quickly to 100. And then it's going to stay at 100 till the kettle or pot of water, whatever it is, boils completely dry, which would take a very long time. And then we go up to 120. So this question has 5 parts to it. We've got part 1, 2, 3, 4, 5. Anytime the temperature is going up, is the temperature. This will be time. There's no real scale there because if it's a really big burner, it's going to heat up fast. If it's a small little candle, it's going to take a long time. But it's just a relative thing here. So for number 1, that's a change in temperature one. So that'll be MC delta T. Step 2, that's a melting one. So that'll be MLF. F stands for fusion, or you can think of it as freezing point. 3 is Q equals MC delta T. And that's just regular liquid water. And then we have to boil the water. And that's the latent heat of vaporization. And the last step I have to heat up steam. Steam has a different heat capacity than water, and ice has a different than water. So we go right in the mass. So the mass, they're all 10 grams. Okay, so they're all, might as well write them in now so I don't forget. And the C value for, well, this one we know. Water is 4,200. That one, we gotta look up all these other numbers. So let's look them up right away. Latent heat of fusion for water, right at the bottom, is 3.3 times 10 to the 5. That's 330,000 joules of energy to melt 1 kilogram. But we only have 10 grams. LV for water is 2.3 million. It takes a lot more energy to boil something away than it does to melt it. You're separating the molecules much further. Okay, let's take a look at steam. Steam is 2020. And ice is right here, 2,116. And let's take a look at the temperature changes. The ice went from -20 up to 0. That's an increase of 20. The water went from 0 to 100. That's an increase of 100. And the steam went from 100 to 120. That's an increase of 20. Okay, we've got all the givens. Everything's in here. Now we just have to do the math. And then I do this way so I can just total it up at the end. So we got 0.01, 2116 times 20. 423.2, and then we got 0.01, 330,000. That's 3,300, and then we got 100, 4,200. That gives me another. Oh, that's 1/100th. That's 100. Yeah, we could have just canceled some stuff out there. We got 0.01, 2.3 million. Is 23,000 joules of energy. And the last one is 404 joules. And if I add them up for a grand total, I get 31,327.2 joules. And I'll give the answer here is off a little bit, so we probably used a different C value for steam or ice. Might not have used the one from the last page there. Okay, so that's the final answer there. That's a big question, maybe on a test. But let's go to number 11. Number 11 says, a 40-gram sample of coliform is condensed from vapor to liquid at that temperature. So that's liquid to vapor, that's LV. So Q equals mLV. They gave you Q. They gave you the mass. The only thing you're missing here is LV. And the question says, what is LV? So let's fill in our numbers then. So I got 987 joules. The mass is 0.040 kilograms times LV. Solve for LV. 9,870 divided by 0.04. And we got 246,750 joules to melt 1 kilogram. Okay, that 0 is missing on the photocopy, so that's the actual answer. And that's it for that worksheet.